My first step is to draw a free body diagram for the tension forces acting on the center ring on the force table. I'm going to use the guide here of one of the tensions being the weight of 120 grams at 225 degrees. So I have to think about the orientation. There's 0 degrees, 90 degrees, 180. So 225 is about 45 degrees below the 180 degree axis. I'm going to draw in a vector here, approximately like this. Let's see here. About like that. And that's 120, the weight of 120 grams in length. And then the next one is a little bit longer, 180 grams and 165 degrees. That's about 15 degrees above the 180 degree axis. And it's a bit longer. Okay, there we go. I'm going to get rid of these little portions here. Okay, my next step is to label these things and think about how I'm going to decompose them. So I do not want their x components to share the same axis here. So I think what I'm going to do is I'm going to use, say, this decomposition. This one is tension 2. And this will be tension 2 in the y direction. Here's tension 2 in the x direction. And then so that this first one doesn't interfere and share the same x component here, I'm going to decompose number 1 this way. So I'm just making this choice using a little bit of artistry to make that happen. And this will be tension 1 in the y direction and tension 1 in the x direction. So I know that this big angle all the way over here was 165 degrees, but I need the internal angle here inside the right triangle, either up here or over here. So I'm thinking to myself, if this is 165, the remainder is 15 degrees to get to 180. So this is a 15 degree angle there. And then similarly, I need one of these internal acute angles inside this right triangle. I'm going to choose this one. So I know this is 180 degrees to here, and it was 225 degrees. So that means that this angle here must be 45 degrees. And so this one inside of here must also be 45 degrees. That's an important part, is that I'm not actually using the given angles for the individual tension vectors. I'm using the reference acute angles inside. Now, the reference angle goes from the x-axis up, and that's not quite what this one is, but I use this reference angle here, 45 degrees, to figure out what this one's going to be, because I know that this big angle here has to be 90. All right, now I'm looking at this thing. I'm trying to figure out where's the third force that'll bring the system into equilibrium. So now I'm just using some intuition. I see that these two tension forces are both pulling to the left. So my equilibrium force is going to have to pull against this one and against this one. So it's going to be a big pull to the right. And then I see that the tension 2 is lifting up a little bit, but tension 1 is really pulling down quite a bit. So I'm imagining that the net pull in the vertical direction from these two is downward. So to balance that, I'm going to have to pull upward some amount. And so I'm envisioning the third tension force is going to be over here someplace. That's where I'm thinking from my intuition. Now let's let the math tell us what's actually going to happen. So I'm going to state an equilibrium. It's a statement, sigma f equals 0 in multiple dimensions. I'm going to break this apart into a horizontal equilibrium and then vertical equilibrium. And there's going to be 3 forces in my sum. So there's tension 1 in the x direction, tension 2 in the x direction, tension 3 in the x direction. And those 3 tension forces have to add up to be 0. Similarly, I've got tension 1 in the y direction, tension 2 in the y direction, tension 3 in the y direction. These are just concept statements here. It's hard to imagine 3 things adding up to be 0 if they're all positive, but it's important to recognize that hidden inside of these symbols here, these vector notated symbols, are directions. And two of these directions go to the left. So those are negative. And then we're going to find out what this one is. So here goes. Removing the vector notation. T1x is here. It points to the left with the strength T1x. T2x is here in the diagram. It points to the left with the strength of T2x. The T1x and T2x now represent the magnitude of the x components of those two vectors. Now this is important here. I think T3x points to the right for my intuition. This is where I think T3x points. But I'm not going to influence my mathematical reasoning with my intuition. I'm going to try to support my intuition with the mathematical reasoning. So I'm going to leave this as T3x as a vector and see what it tells me. So now let's take a look. I'm going to do some algebra and try to solve for the third x component. So I'm going to then leave T3x on the left side of this equation and add T1x to the right and add T2x to the right. Let's see if this makes sense. These two scalars are adding together to be some value that's equivalent to the left pole here and the left pole there. And then the sum of those two things is positive. So the direction of T3x is positive, and the amount of pull T3x has to have is equal to the amount of pull these two have, which was to the left before. So this is making sense. Now the physics is done. Like this is the line of physics right here. Now let's do the math. So here's T3x. T1x here, it's far away from that 45-degree angle. So I'm going to use the sine function. All of T1 and the sine of 45 degrees. There's the plus sign. Here's T2x. It's here in the diagram. I'm going to use the cosine function here because it's close to 15 degrees. So it's all of T2 and it's cosine 15 degrees. It's important that we don't always think of the x's and cosines going together and the y's and sines going together. Depending on how you form your triangles, the length of the side opposite to the angle is a sine function, and the length of the side that's close to the angle is a cosine function. Now I'm going to calculate those values. The weight of 259 grams. Now let's try the same thing for the y component. So I'm looking on the diagram. I see T1y is here, it points down. So it's negative in direction, T1y in strength. T2y is here on the diagram. I see it's positive in direction, T2y in strength. And similarly, I think T3y points upward, but I'm not going to let my intuition influence my mathematical reasoning. So I'm going to leave this as T3y, set that equal to 0. And use algebra. So that's the line of physics right there. It's kind of done. I'm going to use my algebra, T3y vector, leaving it on the left side of the equation, adding these two to the other side. So T1y minus T2y. T1y is close to the 45-degree angle. So it's all of T1 and a cosine function. There's the minus sign, and T2y is here. It's opposite to the 15-degree angle. So I use a sine function. And now I'm going to calculate. So this is 120 cosine 45 minus 180 sine 15. .3, the weight of 38.3 grams. There's the y component of T3. So now the next thing for me to do is to compose the third vector. So I'm going to draw the third vector. I'm going to take I got a positive x component and a positive y component. So I've got a positive x component that's nearly 260 grams of like that, and then about 33.8 like this. So trying to scale it proportionally correctly. And then that will be T3y, T3x. This will be T3 here. And this particular angle will be the third angle. So it's going to be a first quadrant vector. Does this make sense? Yeah, I was kind of envisioning something like that at the beginning. That's good. So my intuition and my mathematical reasoning are supporting each other. It's good. Now let's find out what T3 is. So T3, using the Pythagorean theorem, it's T3x squared plus T3y squared. And that turns out to be 262 grams. And then this angle is going to come from the inverse tangent function of opposite over adjacent. So the y over the x. And take the absolute value of this, come up with the inverse tangent of 38.3 divided by 259. It's 8.41 degrees. So now I can state the equilibrium force will be equal to the weight of 262 grams at a direction of 8.4 degrees. Now I'm going to set it up on the force table. Let's see if I can get it to work.